Lesson 44, Regression Analysis. Regression analysis is a powerful statistical analysis technique. In a regression analysis, data from the past, that is, existing data, is used to observe a pattern that can be modeled mathematically, which, when appropriate, can be used to predict the future, that is, as of yet unknown data values. Regression analysis reveals existing relationships between variables in order to use the value of one variable to predict the value of another variable. Whenever the primary focus of the issue under investigation involves predicting a certain data value when given some related information, a regression analysis is conducted. So in a regression analysis, data from the past or existing data is used. Pairs of data values are collected from each subject in the sample with the intention of predicting one data value, called the predicted, based on the other data value, called the predictor. Now, data from the past is used to observe a pattern. A scatter plot can be constructed using the pairs of data values in order to identify any existing patterns or trends in the sample data. If a specific pattern is identified in the data, the regression analysis attempts to model it mathematically. A mathematical model is a function, y equals f of x, that resembles the pattern exhibited by the pairs of data values, where x is equal to the predictor and y is equal to the predicted. A scatter plot displays the pairs of data values, x, y, as coordinates. So if all the pairs of data values are plotted in a scatter plot, we can reveal the pattern in the data. In this case, if the data points all seem to follow closely a linear relationship, a linear regression model can be applied. The linear regression model takes on the form of y equals a times x plus b, where a is the slope of the line and b is the y-intercept. On the other hand, if the data points take on a pattern which resembles a parabola, the quadratic regression model can be applied. The form of the quadratic regression model is y equals a times x squared plus b times x plus c. But if the pattern in the data takes on values where it seems to grow exponentially, the exponential regression model can be applied. The exponential regression model takes on the form y equals a times b raised to the x power. Or the pattern observed in the data can take on a curve which seems to follow a logarithmic curve. In this case, we can use the logarithmic regression model, which takes on the form of y equals a plus b times the natural log of x. So in any case, once we've observed the pattern in the data, and we've identified which model that we want to model it mathematically, we can then use regression analysis to derive at that mathematical model. But before we use this mathematical model to make predictions, we need to determine if it's appropriate to do so. A statistic called the coefficient of determination is calculated to determine whether it is appropriate to use the derived regression model to make predictions. It is appropriate to use the derived regression model to make predictions whenever the calculated coefficient of determination is close to the number 1. 1 indicates that 100% of all the data points fall exactly on the regression model. Once it's determined that it's appropriate to make a prediction, we can use the regression model to predict the as of yet unknown future values. The predictor variable x is being used to determine the predicted variable y in the regression model. This is done by taking a given value of x and entering it into the regression model, y equals f of x. The resulting value of y, which is calculated, is the corresponding prediction. Depending on the nature of the relationship between the predictor and the predicted variables in the regression analysis, there exists numerous regression models that can be derived. As an introduction to regression analysis, only the linear regression model will be presented in this lesson. The guide provided here can be used as a reference anytime a linear regression analysis is being conducted. A linear regression analysis is used to predict one variable based on the linear relationship with another variable. A linear regression analysis can be conducted using the TI-84 calculator. To do this, we need to enter the predictor data, the x, into list 1, and the predicted data, the y, into list 2. After the predictor and predicted data have been entered into separate lists, the linear regression command on the TI-84 calculator, which is abbreviated LIN-REG-AX plus B, calculates the slope, A, the y-intercept, B, and the coefficient of determination, R squared, for the linear regression analysis. Note, in order for the R squared to be displayed, the statistics diagnostics mode must be set to on. I will demonstrate how to switch the diagnostics mode to on the TI-84 calculator. Just realize that this only needs to be done once, because once the statistics diagnostics mode is set to on, it will remain on even when the calculator is turned off. To do this, we press second catalog, which is the number 0. The catalog is an alphabetical listing of all the commands in the TI-84 calculator. Arrow down until the cursor is next to Diagnostics On. With the cursor next to Diagnostic On, press Enter to select, and then Enter to execute. So now it's done. So you will not have to do it again unless the diagnostics is switched off. Now to enter data, we press Stat Enter. And the predictor data is entered into list 1, and the predicted data is entered into list 2. Then the linear regression command is found by pressing Stat, arrow over to Calc for calculate, and then arrow down to LIN-REG-AX plus B. Press Enter. Then we have to give the calculator the lists, second 1 for list 1, comma, second 2 for list 2. The lists are always entered in the order of x, comma, y. Pressing Enter calculates the linear regression results, where A is the slope of the regression line, and B is the y-intercept of the regression line, and R squared is the coefficient of determination, which is used to determine if it's appropriate to use this linear regression model to make a prediction. Here are the formulas the TI-84 calculator uses for calculating A, the slope, and B, the y-intercept of the regression line. Using these calculated values for the slope A and y-intercept B produce the best predicted value of y based on x, which is denoted by the symbol y hat. Y hat is considered to be the best predicted value of y based on x because it minimizes the total of all the squared prediction errors. That is, the linear regression model that will best predict y based on x is given by the form y hat equals ax plus b, produces the regression line that is as close to all of the data points as it can be. Now, b, the y-intercept, is calculated by taking y bar, the mean of the y values, minus a, the slope of the regression line, times x bar, the mean of the x values. A, the slope of the regression line, is calculated by taking s sub y, the standard deviation of the y data values, dividing by s sub x, the standard deviation of the x data values, and multiplying that by r, the correlation coefficient. This is the formula for calculating r. The linear correlation coefficient r measures the strength of the linear relationship between the variables x and y. R takes on positive values whenever the slope of the regression line is positive. Thus, positively correlated variables change in the same direction. That is, when the x variable increases, the y variable also increases. R can take on negative values whenever the slope of the regression line is negative. Negatively correlated variables change in opposite directions. So when the x variable increases, the y variable decreases. The square of the linear correlation coefficient, r squared, produces the coefficient of determination. Here, the coefficient of determination r squared is rewritten in a form that can be interpreted more easily. The coefficient of determination r squared measures the proportion of the variation in the data that is explained by the regression model. It does this by taking the numerator, which measures the variation in the data that is explained by the regression model, and dividing it by the denominator, which measures the total variation in the data. Whenever all of the variation in the data can be explained by the regression model, we get the total variation divided by total variation, which equals 1. So a coefficient of determination r squared equals to 1 means that 100% of all the data values are explained by the regression model. On the other hand, if none of the variation in the data is explained by the regression model, then r squared is equal to 0 out of the total, which is 0. So whenever the coefficient of determination r squared equals 0, that's an indication that none of the variation in the data is explained by the regression model. So the coefficient of determination r squared takes on values anywhere between 0 and 1. When r squared is close to 1, the linear regression model fits the sample data very well. Hence, it can be relied on to make predictions. When r squared is not close to 1, the linear regression model does not fit the sample data. Hence, it should not be used to make predictions. So when the coefficient of determination r squared equals 1, this indicates that 1 or 100% of all the data points fall exactly on the linear regression line. In this case, using the linear regression line to make predictions will lead to perfect results. But when r squared is close to 1, like 0.99, in this case, you can see that just a few of the points fall slightly away from the regression line. In this case, it's still appropriate to use this regression line to make a prediction because it very closely models the linear relationship in these variables. Even at r squared values of 0.9484, you can see that the sum of the data points fall a little bit further away from the regression line, but still this overall pattern can be used to make good predictions. A coefficient determination value r squared of 0.8469 looks like this. Here you can see there's a little more variation of the data points around the regression line. Still, the linear regression model does a pretty good job of making predictions in this case. When the coefficient of determination r squared is in the range of 0.7631, we can see that there are several more points further away from the regression line. Even though the pattern is still exhibited here, it can be used to make a prediction. It's just not as accurate when the r squared is much closer to 1. But as the r squared value gets further and further away from 1, the data points scatter further and further away from the regression line, meaning that this regression line should not really be relied on to make very accurate predictions. Finally, when r squared equals 0, that's an indicator that 0 or none of the data points fit a linear relationship in this model. So in this case, there's absolutely 0 or no linear relationship between the predictor variable x and the predicted variable y, thus leading to an r squared of 0, which tells us that we should absolutely not use the linear regression model to make a prediction. A linear regression analysis can be conducted with random sample data that exhibits not only a linear relationship between the variables x and y, but also the y variable must follow an approximate normal distribution with similar standard deviations for each value of x. Statistically, there exists hypothesis test procedures to check for these conditions of the y variable following an approximate normal distribution and a hypothesis test to check whether the standard deviations are equal or not. But for the purposes of this lesson, we'll just be conducting our linear regression analysis under the assumption that the y variable follows an approximate normal distribution with similar standard deviations. So now that we've learned how to conduct a linear regression analysis, let's apply what we've learned in some examples.